Introduction to Robotics course. Today's topic is the mass moment of inertia. The mass moment of inertia is a measure of the ability of an object to resist change in its rotational speed about a given axis. Therefore, you can think about it as the rotational inertia of that object about the given axis or a specific axis. And at the same time, you can also think about the mass moment of inertia as a measure of the distribution of mass of an object with respect to a given axis. Notice that in all of the three definitions, we had to mention a specific axis or a given axis. So we agreed that mass moment of inertia is a measure of the ability of an object to resist change in its rotational speed about a given axis. And what comes to our mind now would be mass, because if you recall, mass is also a measure of the ability of an object to resist change in its velocity. Therefore, we would anticipate that the role of mass moment of inertia in rotational mechanics would mirror the role of mass in linear mechanics. Here in this table, we have formulas for the linear mechanics and the formulas for angular mechanics. So for example, in Newton's second law of motion, we have the force is equal to the mass times the acceleration, whereas in angular mechanics, we have the torque equal to the mass moment of inertia times alpha, which is the angular acceleration. Momentum, linear momentum, is mass times speed. Angular momentum is the mass moment of inertia times angular speed. Kinetic energy, here it's going to be in linear motion, it's going to be half mv squared, whereas in angular motion it's half I omega squared. Again, omega is the angular velocity or angular speed. Now let us consider a point mass. A point mass is basically a very small particle, and we assume now that it has a mass m. The mass moment of inertia of this point mass is equal to the mass of this particle times the distance from a reference axis squared. And accordingly, you can see that the units of the mass moment of inertia would be kilograms times meter squared. To give an example of the importance or the application, one of the applications of mass moment of inertia, consider the high wire artists, where they cross from one building towards another building, and usually they would carry a horizontal pole. And by just looking at the simple formula for a point mass, where the mass moment of inertia is defined as mr squared, you can see that this horizontal pole would really increase the mass moment of inertia of this high wire artist about the vertical axis, about his own vertical axis, because with this pole we have the it's heavy by itself, and it's far away. You can see it's long enough to have its mass distributed and far away from the vertical axis. So we agree that the mass moment of inertia of the artist now is increased by carrying this horizontal pole. And how would this benefit him? If you look here, we have the relationship between the torque and the angular acceleration. And for certain cases, we have no control over the torque, such as for this stunt act, because the torque here would be, for example, certain gusts of wind, and these we don't have control over. So we assume that they are constant or they have a given value. Usually we think about the worst case scenario. Then, and by increasing the mass moment of inertia by using this horizontal pole, in order to satisfy this equation and keep a constant torque or a given torque, so by increasing I, the angular acceleration would reduce, and this way we are reducing the response of this artist to the disturbances in this case. And a similar trick is usually also applied in figure skating, because you see when they spread their arms, usually this way they are increasing their mass moment of inertia, and when they tuck their arms in, what they are really doing is that they are reducing their mass moment of inertia. Up to this point, we have seen that the mass moment of inertia for a point mass is basically the mass times the square of the distance to a specific axis. Now, we would like to extend this to the case of a rigid body. And for a rigid body, we can simply think of it as consisting of a very large number of point masses or particles, each of which has a differential mass or an infinitesimal mass, dm. And in that case, for each small particle or point mass, it will have a differential mass moment of inertia, di, which is equal to r squared times dm. Now, so for the complete rigid body, its mass moment of inertia would be simply the summation of those of the point masses making up the whole rigid body, or simply because integration can be thought of as a process of summation, so simply the mass moment of inertia of the rigid body is going to be equal to the definite integration from 0 to m of r squared dm. This is an important formula because we'll be using it for deriving specific formulas for certain geometries, basic geometries of rigid bodies. For example, here we are asked to derive the mass moment of inertia of a hollow cylinder. As seen here, this cylinder would have a height of h, an inner radius ri, outer radius ro, and what we will do is that we are going to apply this formula here, the general formula of a mass moment of inertia of a rigid body with respect to a certain axis. And the axis, of course, in this case would be the vertical one going through the cylinder here. And we will start by considering a differential ring, one shown here in orange here. And this ring will have a thickness of dr, and it's at a distance of r from the center. This ring will have a mass of dm, and this is going to be equal to the density times the volume of the ring. And the volume of this ring is simply dA, the differential area of this ring, times the h, because volume is area times height. And dA, the differential area, we can think about it as what? Can think about it as the area of the larger circle here with a radius of r plus dr minus the area of the inner circle which has a radius of r. So you can, again, so the area of this ring is simply the difference between the area of two circles, one with the outer radius and one with the inner radius of the ring. And if you square the terms here, so this is going to be r squared plus 2rdr plus dr squared minus pi r squared. And you can see that this term will cancel out with this one here. And dr is a small number. And if you take, whenever you take a small number and square it, it's going to be even much more smaller. So for example, if you take 0.1, if you square it, you're going to get 0.01. And you can see that therefore this can be neglected. And simply the area of this differential ring will be simply 2 pi r dr from this term, remaining term here. Now we want to substitute this back into the definition of the differential volume. So dV becomes 2 pi r h dr, and substitute this in turn into the definition of the differential mass. So we still have rho, and instead of dV, now we have 2 pi r h dr. So this brings us to this formula here for the differential mass of the ring, which is in orange color here. Now substituting this into the definite integration. So we have dm here. So it becomes, because we already have r squared, we have an r here, so we'll have r cubed, and then 2 rho pi and h. All of these do not really depend on r, so they can be taken out of the integration, and you need to perform the integration of r cube, and this becomes because it's definite integration, it becomes r the outer radius to the power 4 over 4 minus the inner radius of the cylinder to the power 4 over 4. And you can simplify this a little bit more, and you will get this formula here. So now we have the mass moment of inertia of a hollow cylinder as a function of its density, pi h, its height, and we have the outer radius and the inner radius. One thing you want to do is to get rid of the density in this expression. And this is possible because we know that the density is the mass over the volume, and here this is the capital M is the total mass of the cylinder, and this is capital V is the total volume. So the total volume is going to be the volume of the outer cylinder minus the volume of the inner cylinder, if you wish. So it becomes pi r outer squared minus pi r inner squared, and of course you multiply it by an h, the height, to make it into a volume. And taking this now and substituting it back into our previous expression for the mass moment of inertia instead of rho. So we have it here now, and you can see that the pi can be cancelled out, h can be cancelled out, and we can do furthermore simplify this expression here. So it becomes the product of r outer squared minus r inner squared times r outer squared plus r inner squared. This will cancel out with this, and we'll end up with the very neat and simple formula for the mass moment of inertia of a hollow cylinder. So now it depends on the mass, total mass, over 2 times the inner radius squared plus the outer radius squared. So here's a summary of what we got here. And if you want to look at a special case where we have a solid cylinder, for a solid cylinder, the inner radius will be 0, and the outer radius, if you wish, we just call it r, and this would become your formula or expression for the mass motive inertia of a solid cylinder. The good thing, you don't need to do this derivation for every different geometry, because this has been already done. So you will find in textbooks and those of the dynamics textbooks and other similar courses, you will find tables that will give you the mass moment of inertia for basic geometries of rigid bodies. We can see, for example, in this case, we have the hollow cylinder that we just derived the formula. In fact, we derived this formula for the mass motive inertia of a hollow cylinder about the z-axis. What you can see, it's interesting here that we can also find the formula about the mass motive inertia about the x-axis and the y-axis. So it's not necessarily only about the z-axis. Here, this is for a solid cylinder, and you can see also for a thin rod and for other different geometries. This is the mass motive inertia formula for a rigid body about a certain axis. And in case if we are dealing with the Cartesian coordinate system where we have the axes x, y, and z, then we can even simplify this a bit more or find a certain relationship, because let's look at Ix. If you are considering the mass moment of inertia of dm with respect to an axis x, so in the formula we'll have rx squared, which is the distance to the x-axis. So we have rx squared dm. And from Pythagoras, we will see that rx squared is going to be in fact equal to y squared plus z squared, because we have this triangle here, right triangle. And the same applies also when we are calculating the mass motive inertia about the y-axis or about the z-axis. So we have these formulas. If you wish, you can think about them as the general mass motive inertia formulas or expressions about the axes x, y, and z of the Cartesian coordinate system. Now, the mass motive inertia in literature or textbooks, usually you will find reference to it in different ways. So sometimes it's the mass moment of inertia, it's the simply moment of inertia. There are cases where they call it the second moment of mass, sometimes angular mass, or rotational inertia. But what is really important is not to confuse it with the second moment of area. So what's the second moment of area? Second moment of area is has this formula in general. We'll have y squared. So if you want to find the second moment of area about the z-axis, it's gonna be y squared dA, and we have the integration over the whole area here of cross section. So basically, the second moment of area is a measure of the distribution of area. Whereas remember, for the mass motive inertia, we were talking about the it's a measure of the distribution of mass. But for the second moment of inertia, we're talking about distribution of area about a certain or a specific axis. Here we're talking about the z-axis. So it depends about the distribution of area about this axis. And to be honest, it's a measure of the ability of a structural member to resist bending about an axis. This you may have covered in the solid mechanics if you already have taken that course. Otherwise, what you need to do to know or understand that this is simply the area moment of inertia, or the second moment of area represents the resistance to bending about a certain axis. And we can usually, for example, the specific second moment of area, the second or the area moment of inertia or second moment of area for a rectangular cross section, for example, is going to be 1 over 12 bh cube. For a circular cross sectional area would be pi over 64 d, which is the diameter, to the power 4, and the curvature or kappa would really depend. This is the in this case m is the moment, and this is the Young's modulus or modulus of elasticity, and this is the second moment of area about the z-axis. So if we increase the second moment of area, we'll have less curvature. So this this was out of the topic, but I find it really very important to really be able to distinguish between these two concepts. One being the mass moment of inertia, and the other one is the second moment of area. So in fact, you will notice certain similarities between the two concepts, the mass moment of inertia and the second moment of area. But at the same time, you have to understand there is a big difference between these two. And so, for example, we can see here the formula. The formula for the mass moment of inertia about the z-axis is here. We have x squared plus y squared dm, whereas for the second moment of area is simply just y squared dA also. And the mass moment of inertia was defined as resistance to change of an object to change in its rotational speed about a specific axis, whereas the second moment of area is resistance to bending about a specific axis. The mass moment of inertia was a measure of distribution of mass of an object relative to a given axis, whereas for the second moment of area, it's a measure of distribution of area of a cross-section relative to a given axis. The units for a mass moment of inertia is kilograms meter squared, whereas for the second moment of area, it is meter to the power 4. Usually, you will find applications of mass moment of inertia in robotics, of course, in dynamics, in vibrations, whereas you will find applications of second moment of area in mechanics of materials, or they call it also solid mechanics. The parallel axis theorem, this is also an important theory that you will find here is useful for finding the mass moment of inertia about an axis other than the one that passes through the center of mass of the object. So if you already know the mass moment of inertia about an axis that passes through the center of mass of the object, you can find the mass moment of inertia about any other parallel axis by applying this formula, where the mass moment of inertia about the parallel axis is going to be equal to the mass moment of inertia about the center of mass of the object plus the mass times the perpendicular distance squared. We're talking about the perpendicular distance between the two axes. Up to this point, we were able to find the mass moment of inertia about the x, y, and z axes. But what about the case where you want to find the mass moment of inertia about another axis, an arbitrary axis, not necessarily one of the principal x, y, and z axes? So, and this would make sense if we have an object, a rigid body, which is free to rotate about any axis. And in that case, we would need to represent the mass moment of inertia. So, for example, if you are looking at the angular momentum of that rigid body, the mass moment of inertia would be represented as a tensor or a matrix, 3x3 matrix, which has all of the information to represent the mass moment of inertia. We have this is going to be a symmetric matrix, and you can see that we have Ixx, Iyy, Izz. These are basically the mass motive inertias about the x, y, and z. And but we also have Ixy, Ixz, and Iyz. These are called products of inertia. The formula for these are found here without derivation, of course. So what you need to do, what you need to understand here is that in the most general case now, if you want to represent the motion of a rigid body which is free to rotate about any axis, the mass motive inertia would be represented as a matrix, a 3x3 matrix with 6 unique components, 3 of which would be called simply the mass motive inertias about the x, y, and z axes, and the other 3 are called products of inertia, one being about xy, yz, and xz. So let's take here a very simple example where we have a cube of steel, and this cube has an edge of about 0.25 meters, and we were asked to calculate the mass motive inertia, let's say about the y-axis. And if you look into the tables that we mentioned before, you will find that there's a formula where I would be equal to 1/12 the mass times twice the square of the edge of the cube. And if we substitute in numbers here, the mass can be calculated by the density times the volume of this cube, and substituting again for A with the side edge, which is 0.25 of a meter. This will give us a value for the mass motive inertia of this cube about the y-axis, or it could be also the x or the z due to the symmetry of this problem, and the value would be equal to 1.25 kilograms meter squared. The reason why I mentioned this example, because I want to demonstrate how you can use certain software to calculate the mass motive inertia for you. For example, for this same cube, if you use Abacus. Abacus is a well-known software for finite element analysis. So if you draw the geometry of this cube and assign the material properties and perform an inquiry about the mass properties, you will see that you will get in addition to the mass and the centroid, where is the centroid located, you will also get the mass motive inertia. And you will see here that we have the components of the mass tensor, the one we discussed before, about the x-axis, y-axis, z-axis, and the products of inertia here. And we got the same values as before, 1.25 about the x, y, and z axes. That's it for today. Thank you.